We are in a linear regression model. So this is our model. We have a functions variable y on the left-hand side, and regressors probably stochastic regressors on the right-hand side, so x beta plus u. And in the chapter before, when we talked about the geometric properties of the square estimator, we did just math, right? So we just assumed a certain a goal function like minimizing the least squares, or a modal condition of the orthogonality of the u's and the x, and then we derived the least square estimator. Okay, so we didn't talk about variances or confidence bands and expected values and things like that. There was no stochastics. This was just math. It was just columns of numbers, right? So now in this chapter, we reinterpret that model in the sense that the u's are not just some given numbers, right, which we use, which we want to minimize, so the residuals from our regression. No, now we say these are random variables. These are random variables, random errors, you know, which some a distribution, right? And if u is a random error, is a random variable, then the y is obviously a random variable because it depends on u. And if y is a random variable, then of course beta hat is a random variable, right? Because beta hat is x prime blah, 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 times y. So obviously, our estimation of beta hat, using the least square, depends on the random realization of these vector of n random variables, which are u. Okay? So now beta hat is not just a number which we calculated from our data. Well, it's just a number, beta hat. Now we say it is a realization of a random variable. We have a function, an estimator, the OLS estimator, the x prime and so on, formula, and that gives us, well, and that results in a random variable, which, of course, we are now interested in the properties of these random variables, beta hat. Right? So the idea is some u realized out there randomly, and this gives us the y's, condition of the x, and depending on the realization of the y's, we estimate, we calculate our beta hat. So if it's a random variable, of course we want that our estimation of beta is somehow, you know, reasonable. It should be close to the true value. The variation should not be too high, and so on and so on. Okay? Therefore, our first step was to show what is the expected value of that random variable beta hat. Right? This random variable has an expected value that makes sense, right? So what we did already is we showed that if x here is in fact strictly exogenous, so it's uncorrelated with all past, current, and future values of u, then we could show that the least square estimator is in fact an unbiased estimator. An unbiased estimator means that the expected value of beta hat is in fact the true value, which we don't know, right? But in principle, we know that we do not systematically under or overestimate the values of the true parameter vector beta. Okay, if you would have a biased estimator, that would mean that we are on average below or above the value. And this is of course something we do not like. Right? We want to be on average on the correct value. Okay, that we showed last week, or 2 weeks ago. I can't remember. So the action was, the interesting thing was actually that on the one side, you know, you remember that result from the bachelor econometric course, and there it was just, you know, a byproduct from the assumption that is often made in bachelor's course on econometrics, that x is not random. So if x is assumed to be not random, non-stochastic, then of course it is always strictly exogenous, because if it's not random, then it's always uncorrelated with some random variable. Right? very special case that we have not random variables. That's easy, right? But and the second good result was that if you look at the proof, right, that's a one-liner here, you see that, well, we didn't need any assumptions about the covariance matrix of the errors. So now we have this list of assumptions. Well, you know, the so-called standard assumption of the linear regression model. But you see already that, that no autocorrelation and heteroscedasticity or homoscedasticity of residuals we didn't need here. You know, there is no covariance, there is no variance of the U's here. Alright? So if we have strictly exogenous regressors, then this is a very general thing. This is the only assumption we actually need. Okay? That's good news. The bad news was that in most empirical applications, it is this assumption that it's not random and that they are therefore strictly exogenous variables of x in x is too hard. Okay? Especially, you know, if you think about dynamic models where on the right-hand side they are lagged values of y. So y depends on yesterday, right? Then by assumption, you know, the strict exogeneity assumption doesn't hold. I demonstrated that in a very easy, very special model where y just depends on y minus 1 and nothing else. Okay, so accordingly, you know, this proves also that if x is not strictly exogenous, then presumably the estimator is biased. Okay, so that's not good news. Okay, so the square estimator, if we have not strictly exogenous variable, may be biased. And this was this simulation exercise, you know, which showed you if we have here x, a lagged endogenous variable, right, then we show by simulation that in fact there is a bias. Here bias downwards. What we also see here from this figure is that the bias seems to get smaller if the number of observations we use for estimation gets higher. Right, here's a theoretical formula which already suggests that maybe this bias is a small sample bias, meaning that it's something which is meaningless for small n, for small samples, where t, the number of observations here, is not too large. But if we are in an empirical application where t is very large, then this is obviously a very, very small number. And you know, we didn't prove that here, although this formula suggests this in the special case. But what we do next is, well, let's think about what happens with this bias if t goes to infinity, in a very general sense. Alright? So, this is here the, so we're going to talk today also about the asymptotic properties of the estimator. Second thing what we did is, we derived the covariance matrix of the least square estimator. And again, you know, if you accept the idea that beta hat is a random variable, then of course, you know, we want to know where the location of that random variable. It should be close to the true value. This is what we just did with the bias thing. And the second, you know, layer of, you know, of assessment, whether it's a good estimator or not, is the estimation uncertainty, so the variance of the estimator, right? Ideally, the variance of the estimator should be very small, right? So, if in conjunction he's also unbiased, that means I'm on average okay, and I'm pretty sure that I'm very close to the true value. If in contrast the variance of the estimator is huge, then there are a lot of fluctuations, sometimes I'm here, sometimes I'm there. Yeah, maybe on average I'm okay, right? But you know, if I have only one estimation, the risk that I'm far away from the true value is high. Okay, so I'm interested in knowing what determines the variance of the estimator and how big it is. So we derived here in this, you know, and again you see, you know, most derivations here are very short and brief, right? So typical matrix algebra cities. So here is just a general definition of the covariance of a matrix. So this has nothing to do with econometrics. This is just plugging in. The only thing we used here is that we, because of the strict exogeneity here, this means strict exogeneity, we have here an unbiased estimator, right? Because in the general statistic formula, if you write down what the covariance is, you have its expected value of the random variable minus its expected value. And, well, so here in very general terms, here is the expected value of beta hat, but we know already it's unbiased. If we have exogenous regressors, therefore we can write down beta. Okay? So here we use the unbiasedness, and then we just plug in the formula, what we know about the least-square estimator, you know, and we multiply it out, and that's it already. Okay? So that is a well-known formula of the covariance matrix of the least-square estimator. I bet you know that already, also from your bachelor econometrics course. So this result is not new, right? So what is worth emphasizing is that in contrast to the unbiased results, here we definitely use assumptions about the covariance matrix of the use, right? So for unbiasedness, it doesn't matter whether they're heteroscedastic or not, right? But here, we definitely use the assumption here, you know, from going from here to there, that the covariance matrix of the use is just the sigma squared times identity matrix, right? Because we look here, this is the assumption we need. So here we assume that the variance of the U's are always the same, and that the U's of different observations are uncorrelated to each other. So this is the ideal case, right? That the U's are really uncorrelated with everything, and you know, and almost elastic even, and so on. Okay. We talked a little bit last week here about, you know, the comparative statics here. What is that? So the major takeaway here, I would say, is if you look at this formula here, you should note that if the regressors in X are highly correlated, right? If they're nearly linear dependent on each other, that is a factor that contributes to increasing variance of beta hat. I showed you this example here for the very special case of two regressors, so a constant and two regressors, right? And then you can derive with the least square formula, just plugging in here the numbers, right? That the variance of beta 2 hat is this here, and that here was just the correlation coefficient between the two regressors. And you see that here from that formula, the higher the correlation between the two regressors, the closer R2, 3 is to 1. Here is then when you subtract something which is close to 1 from here, you have a very small number here that inflates the variance. And it's important that you understand the intuition behind that result. Yeah, and I think this is really, that's really clear, right? Because if you have a regression here, for example, on two regressors, and they are more or less linear dependent, right? So they are very similar, right? Then it's super hard for the least square estimator to differentiate between the impact of one regressor and the other, right? Could be that this coefficient is high and that is 0, or the other way around. It just doesn't matter. The fit is more or less the same because they, you know, you can more or less replace one regressor by the other, right? If you could perfectly replace it, what would then happen? So here is the empirical relevant case that you have highly correlated regressors, like wealth, an income, or whatever, right? So this is very often in practice, right? That you have correlation between the regressors. So that is not good because it increases your uncertainty. It makes it more difficult for the estimator. What happens in the extreme case when you really have linear dependent regressors? Yeah?
Then beta hat isn't estimate.
Yeah, you can revise it.
Because
Yeah, what?
we go back to the
contains linear dependent regressors, it has a full rank, and therefore x prime x is not invertible. Right? So in this case, just do it right. Type in your regression model and haha, type in twice the same variable. Right? So this one actually happens in practice most often, right? If your calculator, if R tells you, I'm not able to calculate the square estimator because of multicollineation, I don't know whether he explains why, but maybe it's just an error, right? Then very often you just have a typo, right? And you type in, something. We talked about this dummy variable trap, I remember, right? Okay. So you see here, right? The smaller, the less invertible that is, the higher you get that variance. All right. So now we talk about the large set of properties. Because this is that's something like endogenous variables. This is something which very often happens in practice. Okay, we want to be able to estimate dynamic models. Otherwise, D-square estimation would really a really restricted thing. Okay, so the hope is that these problems somehow diminish if we have very large sample sizes, which are both very common nowadays in economics. Okay, so what happens with all these assumptions and all these propositions and properties of these square estimators if n goes to infinity? Okay, the relevant concept here is consistency. This is what we discussed last week. So look here, consistency at the first glance looks like a very, very, very strong proposition on the estimator. And look here, so, for every epsilon larger than 0, the probability that my estimator deviates more than epsilon from the true value goes to 0 if the number of observations goes to infinity. It's a little bit complicated, but I think this is the most easier way to explain. Right? So you see here, this consistency property says the only excuse why you are not perfectly certain about the true value given your data and estimation is my sample size is not large enough. Okay, that's the only excuse. Okay, so if you can get, if your estimator is a consistent estimator, then just by increasing the sample size in theory, you could make this probability that you are too far away from your estimator, from your true value, you can make this probability arbitrarily small. Okay? So, small sample size, not enough observation, is the only excuse why you do not just spot the true value from the data. So you see that this is an asymptotic property, so this is something about n goes to infinity, and the notation, which is typically, that's a definition, and typically econometricians and mathematical statisticians rewrite this consistency thing here in terms of the probability limit, or PLIM. They say theta hat, our general estimator, right, is consistent if it converges to the true value. Or you can write it like this. Everything here you understand. Okay, we have one criteria that tells us, or which you can use to show whether an estimator is consistent or not. And this criteria here depends on the so-called, on the mean square error of the estimator. Right? So this actually, you could, maybe you should replace, reorder the slides, right? So mean square error here, this is the definition, very suggestive because it's a mean of the square error, right? If you multiply this out, maybe a nice exercise for you to do this, you see that you can rewrite the mean square error as the variance of the estimator. Here, this is just the definition of the variance, and the bias squared. So you see, in order to have a mean square error of 0, dimensions we use in order to assess the quality of the estimator. First of all, we don't want that it's super far away on average from the true value, so we dislike systematically under or overestimation, right? And you see, it doesn't matter whether we under or overestimate, we don't like both in the same way, we don't dislike both in the same way, and we also dislike uncertainty, right? So if we have two unbiased estimators, we like that estimator both with a smaller mean square error, meaning smaller variance, because it has less uncertainty, less variations around the true value. Okay? So you see that mean square error, but can also be used in order, to compare your different combinations of unbiasedness and low variance, right? And later we will have, so at the end of the lecture, we will talk about estimators, which in some circumstances are preferable. So we talk about biased estimator, which are preferable about unbiased estimator, because they have a much smaller variance. So very often in practice, in econometric practice, you have estimators with a trade-off between bias and variance. So they have a smaller bias, but a larger variance. And then it depends on the application, maybe, which of those estimators you prefer. One criteria in order to choose it is the mean square error. So you see that they are more or less weight both criteria equally. Okay. So now we use the mean square error to show that the estimator here is, so this is something we use, or we can use in order to demonstrate that certain estimators are consistent or not. Okay? Before we do this, for very simple examples, let me come back here to the proof of consistency of the mean square estimator. So this here. So what you see here, you already get used to it, right? If you have a proposition, first look is what are the assumptions we need to derive the proposition. And here you see we're still in the phase, we still use here the assumption, the standard assumptions of no more correlation and no heteroscedasticity in the residuals. And that's important, this is important to emphasize. Here, we are okay with weakly exogenous regressors, right? So for the unbiasedness, we needed the strictly exogenous assumption. And here, we are a little bit more relaxed for this result. We say, what we need is only weakly exogenous. So this here, so that all regressors are uncorrelated with the residuals, but only for the contemporaneous part. Okay. So in our model here, where we had yt is alpha yt minus 1 plus ut. Okay, so then here this would be the regressor, right? And what weakly exogeneity means is that we have yt minus 1 and ut are uncorrelated. Okay? This model here showed us that, of course, yt minus 1 is correlated with ut minus 1. Right? Because if we write down this equation for yt minus 1, we have yt minus 1 alpha yt minus 2 plus ut minus 1. So obviously, yt minus 1 is correlated with ut minus 1. So obviously, this is not a strictly exogenous regressor. And therefore, as we show by simulation, this leads to biased least square estimates. Okay? But if we only need the weakly exogeneity assumption, then it's enough here to have no correlation between the regressor and the contemporaneous piece. And this here, in this assumption, this just requires that you have U's which are free from autocorrelation, so not zero correlated regressors. much more general now. So let's see. So this is the least square estimator. You see that under this assumption, you can show that the least square estimator is in fact a consistent estimator. Okay? So how does that proof works? The proof is not so difficult, therefore it's on the next slide. This is beta hat. We just plug in here what y is. Y is x beta plus u. We multiply out and we have, we already used this term here. And you see, if the blim of beta hat is beta, this is obviously equivalent to that the blim of this guy here is 0. This is what we have to prove. Okay, here's the proof. Okay, so this is to be shown, right? That the blim of this here is 0. The blim of this is this here. So let's look at this. So, and here comes a trick. So first of all, I already told you last week that the blim is an operator which is, it's a one-dimensional operator. So you can't make things wrong, right? It is the blim of a product is a product of the blims, and all these things work wonderful with the blim operator. So therefore, we can rewrite the blim of this is the blim of these two guys. Yeah? So, and then comes a trick. We are interested in the asymptotic properties of the estimator. So, in a way, we have to include, we have to make our terms here, which show here up, we have to make them dependent on n, our sample size, right? Because so far, this is just for a given n. But we want to look at this here if n goes to infinity. And the trick is to inflate this term here in the following way. Look, we multiply this product here with 1 over n, and we multiply this here with n. N times 1 over n cancels out. So this is identical. You see, the trick is that the inverse 1 over n inverted is just n. Okay? So therefore this is just the same. And now we have, now it really makes sense to say blim n goes to infinity. All right. So now comes an assumption that that I didn't mention here, but this is mentioned at the very beginning here, the regularity condition. I already talked about what that means. That means that x prime x is both finite and invertible if n goes to infinity. Recall the dimension of x prime x. X is a matrix that contains our k regressors. K is a fixed number, typically small. Maybe I have 5 regressors or 50 regressors, something like that. Right? N is a number of observations. So this is this is an n times k matrix. And if you take x prime x, the result here is always a k times k matrix. Irrespective how many observations you have, even if you have 1 million observations, so the matrix x is a k times 1 million matrix. Whoa. This product here, x prime x, gives you always a k times k matrix. Right? Yeah?
In my writings, I wrote down k plus 1 times k plus 1 matrix.
Okay, yeah, maybe it's k plus 1. That very much depends on whether you say you have here k regressors and constant,
Okay.
or if you say k. I'm sorry for that. I'm not sure whether the book is always consistent in this respect, right? But this is when you're unsure about k and k plus 1, it's probably this, right? So sometimes it's better to talk about, when I talk about collinearity of regressors, it makes sense to think about real regressors, economic variables, just a constant, right? That's why I often say I have 2 regressors. Actually, it's a modular 1, yeah, shot is, it's a small number. It's a small and finite number. Even if you have the number of observations n goes to infinity, right? If you have 1 billion observations, it doesn't matter. If you have 2 regressors, then it's a 2 by 2 matrix, right? If k is 2, it's a 2 times 2 or 3 times 3 matrix. But of course, the entry of this matrix is the sum and the product of 1 billion numbers, right? But just try it out with very small matrix, and you see, right? How these are to 1 billion numbers, 1 billion numbers, and then you end up, and it becomes only 1 number. Okay, this is how matrix quantification works. So it is not trivial that this thing here is well defined if n goes to infinity. Okay? So this is why it's an important assumption to talk about that it's well behaved. And this means it doesn't go to 0, it doesn't go to infinity, and it converges to an always invertible matrix because we saw invertibility of this thing is needed. Otherwise we can't write down the estimate. Okay? So the regularity condition here we need is actually nothing but assuming that the plim of this matrix here goes to a certain finite invertible matrix we call sigma. Okay, so this is just the name. This is not a new thing. This is just the name of the well-defined plim of this here. The fact that this here exists, this is just what we mean with is it well behaved. Okay? Alright. So this is this times this, and this has to be the 0 vector. Right? So, and now, again, I'm a little bit unhappy about the notation. This here should be a large x. I should correct this. Yeah? Because this is a vector of k's. Right? Look, on the left-hand side, we started with this here. This is a k times, or k plus 1 vector of the entries of the parameter vector. So this is also a k plus 1 vector. So this is a k plus 1 vector of zeros. That's a 1, right? So, and what is not so clear that this is also a k plus 1 vector, right? And if you multiply a k plus 1 vector with a quadratic k plus 1 matrix, the result is again a k plus 1 vector, right? So this here should actually be a large x, but to make it a little bit more clear, here it is just for one regressor here written out, and you see that this assumption here is equivalent to having exactly that contemporaneous uncorrelatedness very similar to this. So this is equivalent here, in other words, with having weakly exogenous regressors. Okay. An example. Let K1. Yeah. So we have a constant and a regressor, right? So we have something like 1, 1, 1. Think about it. So we have. So the assumption is x prime u is 0. What does that mean? Okay. So my aim is to illustrate you what does it mean. How does x prime u relate to x and u are uncorrelated? Okay? So, for the example K1, right, we have a vector of u's, u1, un. We have n observations, and therefore n u's. Right? Now we have the matrix X, and the matrix X is actually something like this. It is, X is, we have the ones for the constant, and then we have x11, x12, We have only one regressor here in this example. So this is x. Yeah? Here are the ones, this is just a constant. And here we have our data for our single regressor. And if we would have more regressors, we would have here x21, x31, blah, 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 blah. So, if this is x, then obviously x prime is 1, 1, 1, 1. And here we have x11, x12, x1n. Right? X prime is the transpose of it. So now multiply that out. What you get is, if you have now this vector of this matrix, you see the dimension works. You have here just the sum of the u's, e's is 0. Oops. You have here the sum of the u's. And here you have u1 times x11 plus u2 times x12, u3 times x13, and so on. So this is nothing but the sum of the x1I times ui. And the sum goes, of course, from E1 to N. Okay? So now you see what it means. If this is 0, then we have that the sum of the u's is 0. Yeah, because the average is 0, right? If we now take the plim of this, the plim of this here is 0, because we know that on average the expected value of the u's is 0, so this average is 0, and if the regressor is weakly exogenous, they are uncorrelated here with the u's. Okay. Okay. So as I said already, it's very helpful when you see those matrix proofs here. If you look at the matrices and think about what's the dimension of that matrix, you know, I could ask you, for example, what is the dimension of this here? And if you say this is the number 0, wrong. It is a vector of k plus 1, 0, like here. It's a vector of 0. So this is a condition for each of the regressors. Each regressor must be uncorrelated with u's. Okay, so this is the proof of consistency. And now I show you two things. First of all, I show you an example for a not well-behaved x1 maps. You know, and it's not by, you know, it's not an accident that the regressor looks weird, right? Because these non-well-behaved estimators are actually, you know, not so common. Okay? So look here. So here we have a regression model, S1 plus 1 over t, and this is a, you know, a wonderful model. You know, in small samples, this estimator is absolutely unproblematic, right? So we know we have an non-stochastic regression. 1 over t means, right? First observation is 1, second observation is 1/2, 1 over 3, 1 over 4, 1 over 5, and so on, right? This is how we interpret this. Okay. So in small samples, for finite n, so even if n is 1 billion, it's finite, right? We can show that the estimator is unbiased. Perfect. Right? And what the problem is, if you multiply out, if you use this here, you know, if you just do this here, but now for 1, 1 over 2, 1 over 3, 1 over 4, blah, 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 and you sum up with x prime x, that you have here, here's x prime, here's x. If you multiply this out for this specific example, right, you see that the result here in the limit is singular. It's a singular matrix. It cannot be inverted. If n goes to infinity. So actually, here I can say t goes to infinity. Yeah? And the intuition t goes to infinity, every new observation provides less and less information about beta 2 because it converges to 0. Right? It gets less and less unimportant. And this is no good for an asymptotic result, for the asymptotic behavior. We are the least square estimator of beta 2. Okay? So the intuition is, with well-behaved this, that if you increase your observation for each regressor, they must come up, so each new observation must provide additionally sufficiently many new information for your estimation. Right? So think about the extreme case, right? Think about, you look at a regressor matrix, that n goes to infinity and so on, but in fact, up from observation 1000 onwards, say, the observation in x remain always constant. Okay? You increase the number of observations, great, but they do not vary. For whatever reason. They remain constant, right? What would that mean if you plug into this x prime x thing here? You will see that this means that, well, there is not enough new observation. There is no new information actually, right? So if they remain constant, the information, if I have one observation or infinitely many of those constant, it doesn't matter, right? So because there is not enough new information in the extra observations, this is the intuition behind this technical assumption here of well behavior projects. Okay? Not, it has to be enough observation, this is the finiteness. No, this is the invertibility, right? So enough variation, but also not too much, right? Because it should not go to infinity, right? X prime x, which you want to solve and want to invert, is x prime x, if n goes to infinity, should not go to infinity. Yeah, and remember, that was our first concern, because look here, if you multiply out x prime x, this is the sum of n products. If n goes to infinity, you have an infinitely large sum, and we all know from that one that infinitely large sums diverge, right? And this is something we want to do out. Okay. All right. So these are the assumptions. This is the consistency. And now let me come back to this. Did we discuss the estimator already? So I guess this is a nice exercise to practice, these concepts of unbiasedness and asymptotically unbiasedness and consistence and all of these things. And this also shows you how useful it is to know that you can prove consistency using the mean square error, right? So if I want you to prove the consistency of an estimator, I want you to show that the variance of the estimator goes to 0 if n goes to infinity, and the bias goes also to 0 if n goes to infinity, right? So MSE goes to 0 if variance of beta hat, or no, come on, that's theta hat, goes to 0 if the variance of theta hat goes to 0 and the bias of theta hat goes to 0. If we can prove these two things, we know the MSE goes to 0 and therefore the estimator is consistent, right? If the bias goes to 0, we are on average okay, and if the variance goes to 0, we know, it's perfect. The probability that we are far away gets smaller and smaller and smaller and smaller. Variance goes to 0 means there is no variance, there is no uncertainty, right? So I'm I'm sure this is my estimator. And if I'm on average on the right place, then I have the right choice, which I have. Okay? So the example, the starting point, okay, so let y1, y2, yn, that's the notation, yeah. IID, so identically, independently distributed variables, right, with expected value of the yt is mu, and variance of yt is sigma squared. Okay? Task is estimate mu from your sample. Estimate the expected value, which is unknown. We don't know mu, we don't know sigma squared. Okay? So you know how to do it. This is statistic 101, row, standard estimator. And it's standard because it's the best. The standard estimator is just take one, mu hat is just 1 over n times the sum of yt. Yeah, if I have observations t1 to n. Yeah, this is what you do if you have n observations and estimate the expected value, you just take the mean of it. Okay? That's what you do in statistic 101. And now look, is this a consistent estimator? Hopefully, otherwise you would have a rubbish statistic 101. Okay, so what is the expected value of mu hat? This is the expected value of 1 over n times yt. Yeah? Because this is the definition of mu hat. So now the only thing I have to know is this is 1 over n. The expected value is a linear thing, so we have here 1 over n. Expected value yt. And this is always mu. So I have 1 over n times mu. This is mu, yes. Okay, these kind of nitty-gritty things here, this is something we should now really practice, right? Because that happens every now and then. Shows the expected value, derives the covariance matrix, and you always need these rules for variances and expected values. Here, in the very special case of we have just a real random number, so no matrix is involved, right? Okay. So that's good news, right? It's actually an unbiased estimator. So even irrespective how small n is, it's an unbiased estimator. Great. And you see, of course, any estimator that is unbiased, so therefore mu hat is unbiased, and this implies that it's also asymptotically unbiased. Okay? Because if it's unbiased for each finite n, then of course also for large n, and even if it goes larger and larger and larger, it's always unbiased. So asymptotically unbiasedness is a weaker assumption than unbiasedness. Okay? Asymptotic, there are estimators out there, and this is one of the idea of this exercise, to show you that there are estimators out there which are biased, but asymptotically unbiased. Okay? So this is the proof of the unbiasedness of this, and now look at the variance of the hat. So what about its variance? So the variance of the hat is a variance of 1 over n sum yt. So now I use the rule that is 1n squared times, come on, I'm quick, okay? So because they are independently distributed, the variance of the sum is the sum of the variances. The variance of yt is by assumption sigma square. Therefore, I have here n times sigma square. You see, this is 1 over n sigma square. This is a well-known law of large number again, right? That the uncertainty goes smaller with factor 1 over n, or square root n if you talk about standard deviations. Well, and what you see is, well, what about the limit? If n goes to infinity for the variance of mu hat. This is the limit of 1 over n sigma squared, and that is obviously 0, because I have here 1 over n. So here is a proof, A, that your well-known estimator of statistic 101 is actually, for the mean of a random variable here, is actually a consistent estimator. It's not only biased, wow, also the variance goes to 0 if n goes to infinity. So if you have really many observations, and if all these assumptions hold, then you can be pretty sure that you can get arbitrarily close with your estimated mean to the true mean. Okay? So, and what you should be able to do is to repeat, more or less, or to adopt this solution here for the standard estimator for these strange estimators. Okay? Could you do that? Maybe we could do it for 1 or 2 examples. Right? So, your choice. Maybe we do not all of them. So,
How about mu 3?
all right. That was not very democratic. That was first call, first get. That's okay.
Someone laughed, so I guess he agrees.
Mystery. Just for curiosity, is this now complicated to you? Difficult? Somehow? Yeah? Alright. So this is something, very often I say, oh, come on, that's only math, that's complicated, blah, 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 but this is something I would say you should be able to do it. Okay? So, okay. What is the expected value of mu 3 hat? Alright. This is the expected value of this 0.1 by 1 plus 0.99 divided by n minus 1, and then we sum up all the others. I'm not sure whether it should be actually T1 or, let's see. Maybe it's a typo. Maybe I think it should be, because I divided here by n minus 1, maybe it's T2, but let's see. Let's walk with this. Okay, expected value of this should be mu, right? Then it's unbiased. Alright, expected value of the sum. This is the sum of the expected value. So this is 0.01 times the expected value of mu1 plus 0.99 divided by n minus 1 times the sum of the expected value of ut t1 to n. Alright? That's it. So what is the expected value of u1? This is mu. Right? By assumption. All the expected values here are mu. So plus 0.99 divided by n minus 1 times. So how many mu's are here? It is n times mu. So we have it should be mu, but it is that. So if this would be 1, great, but it isn't 1. It would be 1 if n divided by n minus 1 would exactly be 1. Right? So it's actually important to have here T1. Okay? So, therefore, this is not mu, and therefore, bias. This is a bias estimate. And you see, it would be unbiased. It would be unbiased if we would have started here with 2. Because then we would have only n minus 1 here, and then n would cancel out and we would have unbiasedness. So you see, if you look at the formula, you see where the bias comes from. See that? The first observation has a too high weight. Right? It is here with 0, with 1, yeah, if n is 100, yeah, we have here 99% this, 1% this, but it is here, it always shows up. It's proof bias estimator. Okay, what is about the limit of that? So, we see already, if we if we take the limit of mu times 0.1 plus n over n minus 1 times 0.99, you see already if n goes to infinity, this goes opposite to 1. So, in the limit, it's mu. So here we have an example for but asymptotically unbiased. Because the bias vanishes if n goes to infinity. But each small finite n, it doesn't be small, for each n, it is a bias estimate. But as n goes to infinity, the bias gets smaller and smaller and smaller and smaller. It gets negligible if n is large. Alright? Questions? What about the variance of mu3 at? The variance is the variance of this guy here, and this is 0.01 squared times sigma squared. Okay. So look, the variance of that, because they are independently distributed, the variance of the sum is the sum of the variances. So I can, like the expected value, I can the variance just plug into the sum. So this goes in the square out, the variance of y1 is sigma squared. And now I have here plus 0.99 divided by n minus 1 squared plus, how often do I have the variance? I have n times sigma squared. Okay? Please ask now, because this is to demonstrate how easy it is if you just apply the classical properties of expected value and variances for independent random variables. Okay? So please ask. Don't ask, because you're shy. Oh. Okay, I give you a second. Alright, this is 0.1 square sigma square plus, yeah, well, 0.99 squared times n divided by n minus 1 square, sigma squared. Okay. Don't know whether that helps a lot. Now I want to know what is the limit of that. So what is the limit of this if n goes to infinity? The first part doesn't depend on n, right? So it's always there. It's always 0.1 square sigma squared. What about the second part? What's the limit of this? Yeah? It's 0, great. Because here we have n squared in the denominator, and here we have only n. So this here goes to 0. Oops. So that's it. Plus 0. Okay. The limit of the variance of the estimated mu3 head is 1 over 10,000 times sigma squared. So, is it a consistent estimator? No. Not 0. Therefore, mu3 head is an asymptotically unbiased estimator. So the first criteria, check. But the second criteria is not fulfilled. It's not consistent. Yeah. The variance is, the variance of the estimator converged against a very small number, right? So it's 1 over 10,000 times sigma squared. This is really, an example, a didactical example, a pedagogical example to demonstrate what is the conceptual difference, right? It's a small number, but bang, it stayed there. It never goes beyond this non-zero number, right? So the variance does not converge to 0. It's inconsistent estimate. Okay? So you should be able to do this for the other ones, right? And we have, I guess we have a lot of variations here with bias and asymptotically does not be consistent in the variance and so on. Okay? Yeah? If you're not able to do that, ask Lea, for example, in the tutorial, or me next week or whatever. That should work with these things. Yeah? It's also fun. For me, it's fun. Okay. Good. So now we know, or after having solved this exercise, you understood the difference and the intuition behind the concepts biasness, asymptotically unbiasedness, and consistency. And why means for error can be helpful to demonstrate consistency. Okay? So, if I give you things like that, you should be able to do things like that. That would be nice. Okay. Now let's go back to practice. So we saw that, well, there are relatively mild assumptions for having a consistent estimate, but yeah, there are cases, where the ordinary square estimator, beta hat, is not consistent. And here's a standard example. And what you see here now is something like also again like a simulation exercise, right? I hope you do a lot of simulation exercises in the tutorial, yeah, in order to illustrate all the results we have here in theory, right? But we see that in practice how it happens. So look here, we have a simple linear regression model. Right? So everything looks nice, but look here, bam. The weak exogeneity assumption of the regressor is violated. So here, the simulation exercise is done in a way to guarantee that the correlation between the error and the x is actually gamma, and here in the simulation exercise, a positive number. Okay? So I have the regressor and it's correlated to the epsilon. This is the true model. So therefore, if you just plug in into these formulas, you can see that this is exactly that number here that determines we plug in, we see that these invertible matrix, where we should be well behaved, it's just Q now. Yeah, it's just a number. And because it's 1 times 1 matrix, we have only one regressor, right? 1 times 1 matrix is a number. So, and we can show that the probability of beta is just this here. That is the inverse of that, Q minus 1, and then the probability limit of the correlation. And now this is non-zero, because we have a correlation between x and x. The correlation is gamma, and divided by that, we see that this here, these are the two parameters that determine the large sample bias. Okay? So look, this is how it looks in practice. So these are the results of our simulation exercise based on these assumptions about the correlation of the regressor and so on. Look here. This is the input of our simulation exercise. Here you see our regressors, and we generated now residuals, epsilon, that are correlated with the regressors. Okay, and you see, yeah, these are our epsilons, which go into our simulation exercise, and you see, yeah, okay, they are positively correlated. The x and the epsilons are positively correlated. This is the input of our simulation exercise. And now we use these x and epsilons to generate our y, right? Here. And this gives us this scatter plot here of our data. So here we have again the axis, and here you see the resulting y's. So, and now you see a very strange thing. First of all, this here is the steeper thing here, this line here. This is our ordinary least square estimate through these scatter plot. Right? As you see, right, that is the model we use to generate the data. Just so the true parameter of alpha is just 1, right? So the beta should be 1, and this here is, so this is the 1. This is the 1, and this is here a steeper thing. So this is what OLS generates. It will overestimate beta. So this is a theory which tells us our estimate will be higher than the true value if we have a positive correlation here, gamma. Right? And a positive correlation here, Q. If these are positive numbers, then it's larger than that. So, and now think about, why that? Why does the least square estimator overestimate in this situation beta? So we overestimate the marginal impact of x on y, right? So in truth, we increase x by 1 unit, and y increases by 1 unit. This is the true model. What the square estimation says is, if you increase x by 1 unit, you increase y by more than 1 unit. Where does that overestimation come from? What is the intuition? How would you explain this to me without a formula? Yeah?
Because if you increase the x, you also increase the epsilon, and the epsilon is also like it's added from the x to.
Yeah, perfect. Exactly, this is right intuition. The least square estimator, remember how we derived it. It was based on a moment condition and then an assumption on the regressor and residual. It was based on the assumption that they are uncorrelated. X goes up by 1 unit, what happens with u? Or with epsilon? The least square estimated things we don't know because they're uncorrelated. Right? But here, they're not. As you perfectly put it, if x gets larger, because of the positive correlation between x and the regressors, there's a tendency that also the epsilon gets larger. So I know if x is high, then epsilon will also be high. This is the true model. But the least square estimator doesn't know that. So if x goes up, then in the data we will see an increase by y by more than 1 unit. Because it does not only response here to the x that goes up, it also responds to the epsilon, which also goes up because they are positively correlated, right? But the least square estimator thinks there is no correlation. So the least square estimator sees, oh, if x goes up by 1 unit, y goes up by more than 1 unit. Therefore, this coefficient must be larger than 1. No, wrong. Okay? This is what happens if you have correlated regressors. But use least square estimator. Not correlated regressors if you have regressors that are not neatly exogenous, that are correlated with the residuals. All right. The problem is, and this is really evil, right? That this problem you cannot see from the residuals, from the data. You know, from Econometrics 101, there typically these chapter, which we also do here, what happens with the least square estimator if your residuals are not homoscedastic, but actually heteroscedastic, or something like that. And then, you estimate this least square just ignoring the fact that they're heteroscedastic. And then you see from the residuals, oh, look here, boom, there is some heteroscedasticity, right? You estimate using the wrong estimator that ignores the heteroscedasticity in the data, but you see it when you check your residual data, right? In this here, inconsistency, there's no chance to see in the data. Because look, these are the estimated, these are again my regressors, and these are the estimated residuals that come from my least square estimation. Look, they are perfectly uncorrelated, right? So it's not that I can use least squares and then check the residuals and see, I have an inconsistency problem. I have to do something else than least squares. No, if you look at the residuals, it will always look like this. And why that? Because,
because the residuals themselves are uncorrelated to each other.
no, that's not. It is that the least square estimation is based on this assumption. Remember, the least square estimator can be reformulated by moment conditions about the residuals and the regressors. If you do least square estimation, you imply that the residuals are uncorrelated to the regressors. It will be always the case because you have used least square estimation, right? So this is not an interesting result. This is by assumption, or by construction, whatever. If you use least square estimation, then the residual will always look like this, right? Because it's a result of the least square estimation. Even if least square estimation is typically wrong in your application, as here, the least square residuals will always look fine. Okay? So this figure here somehow, so this Mickey Mouse simulation exercise here somehow shows you how critical, it is to defend your estimator when someone in the room says, I think you have an inconsistent estimator. Yeah, that's interesting debate, right? Because you cannot just, if someone says, I think it's not okay because you have heteroscedasticity, we will see later, you can show him tests, look here, it's not blah, 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 I can show you that it's homoscedastic or whatever, right? Test for correlation, everything is fine, so you can go ahead. But if someone tells you, I think you ignored some unobserved correlation between X and the true residuals then it becomes difficult to argue. Then you have to argue to explain why you think that your residuals and your regressors are actually uncorrelated. Not as simple as that. Okay, these are the interesting economic discussions that are based on econometrics. Okay. So consistency is not only a minimum requirement for having a good estimator, it's also a very critical assumption. Right? So it's not easily checked. You have to think about it. All right. What to say about that? No. Okay. So now we have everything which is on that whiteboard. Okay. We have unbiasedness and connected into strictly exogenality. We derived the variance and talked about the impact of correlated regressors on that. We talked about the relation between consistency of an estimator, the meaning of it, how to prove that it's consistent or not, and the weak exogeneity of the regressors. Okay, great. Now assume that we have weakly exogenous regressors. Okay, so we can use these squares because it's consistent estimator in that case. And now we think about, well, could we do better? Okay? We already discussed, yeah, it would be nice to have a small bias. Actually, it would be super nice to have no bias. And it would be great to have a variance that goes to 0. Okay, these two things, these square fulfills if you have weakly exogenous regressors. But are there better ones out there? Right? Is there an estimator function that is better than the square estimator? Well, and for that, we prove this theorem, which you also should know from the bachelor course. It's the so-called Gauss-Markov theorem. And it tells you, well, if you have exogenous regressors here, and if the standard assumption about the residuals is 5, so you see here we need freedom of autocorrelation, no heterophility, right, under the standard regression model, then the least square estimator is the best you can do. He is the best linear unbiased estimator. He's best linear unbiased estimator. So if you say, you know what, I want to have an unbiased estimator, right? So I'm only interested in unbiased estimator. All right. One. Second, you say, I'm only interested in linear estimator because we discussed this. You know how nice it is to have a linear estimator. You know, it's easy to see. You know what happens with rescaling of economic variables from euro to dollar and so on by just multiplying that number. So linearity is also great. So it makes sense to say, the least square estimator is unbiased and it's a linear estimator because we can derive it from matrix multiplication, right? Then is there any other matrix multiplication thing which is somehow better than the least square estimator? All right, so what does better mean now? Better, you know, we have, if we go back to the mean square estimator, mean square error, here, look, that was a very convincing criteria to compare different kinds of estimators. Now we say we're only interested in unbiased estimators. So this here is 0 by assumption. So we have two estimators, say the least square estimators and another estimator, and want to know which one is better in terms of mean square error. Then, obviously, we only talk about the variances of the estimator. So if we have unbiased estimators, the only criteria that remains left is the variance of the estimator. We want to have an estimator with a minimum variance, right? So if you have two estimators, calculate the variance estimated 1, calculate the variance estimated 2, compare, make your choice. Which is better? One is better with a smaller variance. Alright, so this is what we do in the Gauss-Markov. The Gauss-Markov says if the standard assumption holds, then the least square estimator is the best linear estimator, and that means that's the best linear unbiased estimator, and that means that its variance is smaller. In other words, if you give me another linear unbiased estimator, I can show you that the variance of this cannot be smaller than the least square estimator. Right? And this is actually the idea of a proof. Right? It looks like, again, we're used to that, right? So these walls, matrices, right? But look here. Let us see whether we can understand the idea of it. So this is a linear regression model. We assume we have an alternative estimator, beta tilde, because we want to compare the square estimator with some alternative estimator. Let's call it beta tilde. So it is a linear estimator. So what we know about beta tilde, we know it's a linear estimator, and therefore we can write it like this. Beta tilde is just some matrix A we don't know, some arbitrary matrix A, maybe, times y. This is equivalent to the assumption it's a linear estimator. Okay, remember the formula of the least square estimator? A was x minus x minus 1, blah, 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 blah. So this A is beta tilde is just the least square estimator. Yeah? Thank you for the smile. Okay. Okay, this is just math. This means if someone tells you it's a linear model, it's a linear function, it's a measure multiplication. Okay, so, but this is not everything we know about beta tilde. We also know it's unbiased. So we know the expected value of beta tilde is just our true value. It's just beta tilde. Beta. Our true parameter vector. Okay, these are our assumptions. Alright? So, look what follows from the unbiasedness and the linearity. If beta tilde, we said it's A times y. So it's A times y is this. And now we multiply out. This times this plus A times u. Alright? Now we take the expected value because we know the expected value of this thing is beta. So we know the expected value of ax beta plus au. What is that? That is ax beta, because this is not random here. Conditioned on x. Plus au. And au, an expected value is of course 0. Because u is not 0. As an expected value of 0. Okay, so the expected value of beta tilde is just this. Okay, in order that expected value of beta tilde is just beta, the unbiasedness, obviously this has to be the identity matrix. So, linearity and unbiasedness of beta tilde implies that this matrix A multiplied with x is just the identity matrix. Alright? So, and now the notation, right? We just introduce D, the difference. We look at the difference between this alternative estimator matrix, A, and our least square estimator. And you can easily see that if you multiply from the right here with x, right, then this is here ax, this is the identity, and here we have also the identity. So dx is 0. This is just a note. Alright? So far, so good. Now, we want to calculate the variance, the covariance matrix of beta hat. Because remember, the covariance matrix is the k times k matrix, or k plus 1, I'm sorry for that. Where on the diagonal always are the variance of the estimator, and on the off diagonal are the So we want to have small variances, so therefore we want to have that these diagonal elements are small, right? Because these are the variances. So let's calculate the covariance matrix of beta tilde. Okay, beta tilde is just AY. Okay, y is x beta plus u. X is not random here given on x. Beta is not random, so what remains is the variance of AU. U is the only thing that's random. So what is the variance of AU? This is one of those rules for matrix. If you multiply a matrix on the covariance matrix, right? We already use this, you know. The variance of 5 times x is 5 squared times the variance of x. This is a one-dimensional special case of this. Yeah? You see also, if you multiply here with a, the a comes somehow as a square. It's not only one, it's not just a times this, it's a times this, a transpose. This is the rule. Okay? So the variance of u is by assumption the diagonal matrix. So this is just sigma square a prime. And now you use that a is just, if you bring this on the other side, a is d plus this thing here. So we just replaced a with this rotation here. And then we multiply out. D times d. D times this. So this is all this. This is just multiplying out. Okay? And if you have multiplied this out, you end up with this. And now, this guy should be known to you, right? This is the covariance matrix of the least squares matrix. On the left-hand side, we have the covariance matrix of the alternative estimator. On the right-hand side is your covariance matrix of the least square estimator plus something. Alright? So if we take the difference between the two, so the question is, what happens with this matrix? What kind of matrix this is? And this is something we will discuss next week, how to compare matrices. So we have again a little bit about matrix algebra, and the term definition which we talk about a lot is positive derivative. You know that term? You might know that from microeconomics already, or from math. If we talk about, do you have some application where the term positive definiteness of a matrix is relevant? Some examples? Need not to be econometrics. Multivariate optimization. Did you do that in your bachelor? So who did the bachelor at Gefei-FIONA? Because I do it. In the first semester, you know, multivariate optimization, you have a function only from one variable, but from several variables, right? We want to optimize it, right? This is something we do extensively in microeconomic analysis, right? So, and then we have these partial derivatives, and the matrix that gives you, that tells you whether it is a minimum or a maximum in your multivariate function. This is a matrix of the second derivative, it's called Hesse matrix. And the criteria that decides on whether it's a minimum or a maximum or nothing out of it is positive determinism of the Hesse matrix. Okay, so let's talk about that more in detail next. See you.